Hello everyone, this is Dr. Hopkins narrating the next video in our series. And in this case, we're going to look at the thermodynamics of mixing gases together. All right, so let's start out. We're going to do two ideal gases, so we'll make them very easy. And we'll just generally call one A and one B. Okay, and so on one side of, if you want to think about this as like a reaction, on one side of the reaction we have separate A and we have separate B at various pressures and temperatures. And then when we mix them together, then we have A and B mixed together with partial pressures of A and B. And we're going to, because they're ideal gases, then the total pressure is the sum of the partial pressures, just like Dalton's law. Okay, so if we want to know the thermodynamics of that process, is it going to be driven, is this process chemically driven? We're going to look at the chemical potentials before mixing and after mixing. So let's set those up. On the left-hand side, we have them before mixing. We have this little zero at the top of that. That's just the unmixed gas. All right, and then the chemical potential with the star is a reference standard state. Okay, so we always compare them to some kind of standard state. And so we have for A and B before we mix them, and then just the mu A and mu B is after they're mixed. And so here we have our partial pressure, here we have the total pressure of each. Okay, so those are our chemical potentials. Now let's do some mixing. Okay, so the delta G of the mixing, now remember the chemical potential is just the partial Gibbs free energy, so they're related. Right, so the delta G of mixing just tells us whether something's spontaneous or not. It's products minus reactants. And so we can set this up, number of moles of A, number of moles of B in the products chemical potential, and then number of moles, the reactants chemical potential. And so we can substitute in all of those four equations from the last slide into mu A and mu A 0. And we put these in here, and they're minus and plus. And you'll notice, so this is going to cancel with this, so we're going to get rid of all of our reference state chemical potentials. And these natural logs, we can invert them to make them positive, so they would P star over P, and then put them together, and the P stars are going to cancel. And so what we end up with is a simple expression where we have number of moles of A, RT natural log, the partial pressure of A over the total, partial pressure of B over the total. Okay, well we know from Dalton's law that the partial pressure is related to the mole fraction of A and B, and the mole fraction, here we have our definitions, the number of moles of A and the total. So if we substitute these two in here, we're left with the delta G of mixing is just the number of moles overall. Okay, so we substitute all of that in there. Number of moles overall times RT, and it's the sum of the mole fraction of A times the natural log of the mole fraction of A plus the mole fraction of B times the natural log of the mole fraction of B. Or if we had more than two substances, so very general, the delta G mixing is just the sum of all of these components. Mole fraction times the natural log of mole fraction. Now remember, the mole fraction in a mixture has to be less than 1. Okay, so what that means is that the natural log of the mole fraction is always less than 0. It's always negative. And that means that our delta G of mixing is always less than 0. Temperature is always positive, right? And then the x, natural log x, is always negative, that part of it. And so essentially, the free energy of mixing, the gases are miscible at all proportions. So it doesn't matter whether it's 0.1, 0.9, 0.9, 0.1, and any combination between those, all gases are miscible in all proportions at all temperatures. Okay, so let's look at what's driving that. So we'll remember that the partial derivative with respect to T of delta G mix, or delta G, doesn't matter, is minus the entropy of mixing. And so we can do that math. I don't show the equation, but remember it's nRT, sum of the x, natural log of x. So the partial of that is just this, and we add the minus sign. So This part is minus, this part is minus. It's always greater than 0. So in other words, entropy for mixing is always going up. Remember, and that's second law of thermodynamics, entropy wants to go up. This is also, if you want to think about it, kind of intuitive. If we took two pure substances and we mix them together, we're going to increase the entropy or the disorder in the system. So if you want to think about it, entropy is driving this process. And just to show that it's not some other process, some other part that's driving the process, that it is entropy, we can rearrange our delta G, so G equals H minus Ts, and then we can rearrange the expression, so our delta G of mixing, or excuse me, our delta H of mixing, or enthalpy of mixing, is delta G mix plus T delta S, which if we substitute that in, that's equal to 0. So there's no enthalpic driving force. Remember, we are talking about ideal gases, so we're assuming no intermolecular interactions, so there's no chemical reason we should have enthalpic driving forces. We also have the partial derivative, the second partial derivative with respect to P. Of course, there's no pressure in our delta G of mixing expression, so it's equal to 0, but that's also equal to the delta V of mixing, which we already knew intuitively. Ideal gases, the volume of the gas doesn't matter. So if we do that, then we can substitute in for delta U, which is delta H minus P delta V, right? So from our original definition of enthalpy, and the delta U of mixing is equal to 0. So there's no energetic drive, there's no volume drive, there's no enthalpy drive for this process. It's completely driven by entropy. And if you want to think about this, so since it's entropically driven, if we have a two-component system, if we're looking at delta G, the minimum of the delta G mixing, so that's where it's most spontaneous, is where you have an equal mixture of each one of the components, right? And at the end, at x equals 0 and x equals 1, we have 0 because we have no mixing, we have pure components. And it goes down as we increase the mixture, right? And then corresponding, the delta S mix goes up and its maximum, so the maximum entropy is when we have half and half of an ideal gas. So that's the thermodynamics of mixing of gases. Next time we're going to start talking about something a little more interesting, which is mixing liquids.